All right, so we're now recording, and the reason now is I'm here. I want to take your questions. So again, just as a reminder, the exam that is on the screen, the one that was on Blackboard, that is the official practice test. Like I said, there was a little bit of a mess up there on my part. I put two different practice exams up, one in a different one in Top Hat than in Blackboard. This is the one that we're going to be working off of. Are there any things that you want to go over or talk about related to these first three modules getting into this first exam? So I'll open it up for anybody. Anybody have a question that they want to go through first? Right, go ahead. Sure. So that won't be present tomorrow because balancing equations is part of module 4, and this is modules 1 through 3. However, there is a similar trick that we would use when making chemical formulas that is relevant to this exam. So when I get into questions like this one here on number 12, what element forms an ionic compound with the formula Na3X? What I can do is, when we talked about the idea of nomenclature and of looking at charges, remember that we said that, from the periodic table, we can determine the charges of certain kinds of elements. And so, for example, we know that sodium, because sodium is in group 1, that it carries a +1 charge. Now, logically speaking, we could look at this and say, okay, well, if sodium's +1 and there are 3 +1s, then X must be -3, because to balance out all 3 of the positives, I would need 3 negatives. And since there's only one X, that means that all 3 of those negatives would have to be on that X. And so from there, I would go, okay, well, -3 charge, that's group 15, and phosphorus is in group 15. That must be the correct answer. But another approach to this would be simply to look at the subscripts themselves now. Like I was saying, we can reverse this now that I've got a good pen going here. If I were looking at this formula and a three So if I was looking at this formula here, Na3X, the other way I could do this is subscripts and charges can reverse themselves here. So the subscript tells me that the charge is -3. This subscript tells me that the charge is +1. So if I didn't have the periodic table to back off of here, I could infer the charges that way. And similarly, if I had a compound here that I did not know its formula, I could look at the charges and say, okay, two charges the same, it's a 1-to-1. Two charges different, cross them to get the correct formula. So not quite the same, but it is a different subscript trick that is relevant to what we're going to be seeing tomorrow. Now for that one, more practice, we'll be able to see that more often, because as we balance more and more equations, that's the kind of stuff that'll just pop up more and more often as we do. All right, other questions to look at and consider?
Looking at 21, what is the thought process to solve that problem?
Okay, when I wrote this lab question, it was with a couple of things in mind that were similar to what you had done in lab, plus bringing on early concepts of module 1. So we're told that we have an empty 25 milliliter volumetric flask. It has this mass. We then fill it with pellets, and the mass becomes that. Then we fill the flask to the mark with methanol, and the total mass is this. And so what it wants to know is, what is the density of the metal? And so what we have to look at is that there are basically 3 things going on here. To find the density of the metal, remember, by definition, density is the mass of a substance divided by its volume. Well, right now, I don't know the mass or the volume of this methanol. Now, for the mass, or for the metal here, for the mass, I do have some data that I can use. The mass of the metal with the pellets was 130.278 grams. The mass of the flask itself was 20.550 grams. Well, the difference between those two would be the mass of the metal itself. So do a little bit of subtraction here, 130.278 minus 20.550, I get 109.728 grams, and that would be the mass of that metal. Now for the volume, it's a little bit more complicated. We know that we have an empty 25 milliliter flask. And so we know that when we fill that volumetric flask up, it's going to be equal to the volume of the metal and the volume of the methanol that is used to fill it. Now, I don't know the volume of the metal, but I can figure out the volume of the methanol. But again, it's going to come to us indirectly, because all I have is a mass value and a density value. To figure out the mass value, I need to do another subtraction. 142.419 grams minus 130.278 grams. So again, the difference between those two measurements is one had the metal and the flask, one had the metal and the flask and the methanol. So the difference between the two is just the methanol's mass. 142.419 minus 130.278, 12.141 grams of methanol is how much methanol there was. The next step would be to turn this into a density, or I'm sorry, use the density to turn the mass into a volume. So 0.7918 grams in 1 milliliter. So if I divide that by 0.7918 to 4 significant figures, I get 15.33. So now I know that the volume of the methanol is 15.33 milliliters, which means that the volume of the metal would be the difference of these two, 9.67 milliliters. And so now I have a mass of metal and a volume of metal, dividing them by each other would give me the density . 11.3 grams per milliliter. So this one, yeah, you're right. This one had some layers to it. You had to be able to take the individual parts and pieces. And so there is some of this stuff that you did do in the lab. Now, when you took densities of solids in lab, it was considerably easier. You measured out the mass of the metal. You took the volume of a liquid, added the metal to it, took the volume again, and subtracted the two and carried it out. This was a little bit more significant. So just as a reminder, this key, which has every single problem worked out, will be posted on Blackboard and on Top Hat after the review session. So if you didn't get it here, if you weren't following along, just remember that it will be there as well. All right. Other questions, things that we want to talk about and go over? All right, go ahead.
Question number 17. I don't know if it's like the whole thing.
All right, which statement regarding emission spectra and the hydrogen atom is incorrect? All right, first one, electronic transitions in the atom are quantized. That is definitely true. So remember, quantization is the reason why we have those spectra in the first place. We talked about the idea of continuous energy versus discrete energy. The fact that those atomic spectra give us just these individual lines as opposed to this continuous spectrum is the very reason why we were able to conclude that the energy of those electrons was fixed. That it wasn't an electron can be anywhere. It had to be at a very specific energy to give us those very specific lines and wavelengths. And so that goes along with B. B is another description of atomic spectra. You have discrete wavelengths of light that can be absorbed and emitted. Because if an electron absorbs a photon of light, it has to be able to jump to the exact amount of energy to get to that next energy level or get to a new energy level, however many energy levels above. It cannot give more, it cannot get less. It has to land exactly on the energy level target. And so if the absorption spectrum is at 450 nanometers, it will accept a photon at 450. It'll emit a photon at 450. It will not at any other frequency. So change that 450 to 455, not going to happen. Now it doesn't have enough energy to get over to that, to get up to that energy level. Moving from 450 to 445, not going to work anymore. Now it has too much energy. It actually leaps over. So you have to have that specific amount of energy. Atoms can absorb all wavelengths of light, but only emit photons of certain energies. That's where we're wrong, because that's the exact opposite of what I just said. Remember, if that was the case, think about it. We looked at emission spectra versus absorption spectra, the dark lines versus the bright lines. Notice that, remember that those lines were always in the same position because the atom could only absorb that very specific photon and emit that very specific photon. It couldn't emit and absorb in between. Otherwise, that dark line spectrum would be all dark lines because it would be able to absorb anything. It doesn't. For the most part, it transmits most energies. It absorbs some, it emits others. Well, emits the same. D and E are just kind of attributions. Balmer did prove that hydrogen had a wave-like nature. And the reason we could say that is because we knew that the spectra existed. Balmer looked at specifically the visible spectra. Balmer and Rydberg developed empirical equations to fit experimental data. Yes, that's the exact equation that we used to calculate those wavelengths, calculate those energies. So it was only C that was really, truly incorrect. Right. Other questions or concepts just in general that we want to go through? Sure. So just in general? Okay. So what we have to remember about quantum numbers is that there are 4 digits that detail what a quantum, there are 4 digits that detail electrons. And remember that the quantum numbers go from generic to specific. So the first quantum number, the principal quantum number, that's the most generic quantum number. That's the quantum number that tells us what energy level our electron is in. And that's all it says. It says that that electron is in this energy level. So when we describe electrons by the principal quantum number, we could be describing several different electrons by that quantum number exclusively. So that's N. N is the top of the funnel. As we come down, we get to L, the angular momentum quantum number. L takes that energy level and breaks it down to a sublevel. Those sublevels we know by their shape. Spherical for S, dumbbell for P, cloverleaf for D, and crazy for F. So we've gone from every possible electron in a given energy level to now a subset of those electrons in one of those sublevels. And how many electrons are we talking about? It depends on the sublevel. So for S, we're talking about 1 of 2 electrons. For P, we're talking about 1 of 6 electrons. For D, we're talking about 1 of 10 electrons. For F, we're talking about 1 out of 14. That's the L quantum number. Now, for L, what we have to remember is that there's a key to it. The key has to do with what number corresponds to what sublevel. So for L, we primarily talk about these 4 sublevels, and they correspond to these sublevel shapes. Where we get confused a lot of the time is in trying to figure out what that n-1 thing means. Because most of the questions, most of the issues that we had on the quiz related to quantum numbers were that, where I might tell you, okay, you've got a 5p orbital, and so okay, well, that means n equals 5 and p equals 4, or L equals 4, because L is always 1 less than n. And that's not the case. The limit of L is n-1. The highest it can be is n-1. So in this case, 4 is the maximum for that 5th energy level. But the designation, P, tells us that our value of L is equal to 1. So when we're describing a sublevel like that, 5P, 4D, 4F, 3S, whatever it is, that first number is our value of N. Tells us the energy level. That second letter should give us the value of L, because that value of L is fixed based upon the type of orbital that's there. The only place where n-1 comes out is if we're looking at questions like this one, where we're trying to figure out if I have a valid or relevant set of quantum numbers. Because in those cases, yes, we start to look at, well, is there such a thing as the 2F sublevel? And the answer there is no. And the reason why we know the answer is no is because if I'm looking at the second energy level, the maximum value of L is 1, and 1 would be the P sublevel. So the 0 and the 1 are possible, which means that in the second energy level, I have 2S and 2P and nothing more, which goes along with our electron configurations. 2s2, 2p6, and then we move on. There's no 2d10, 2f14. Those numbers don't even register because those orbitals don't exist. It's not that they're high energy, they just don't exist, period. So that's L. M sub L, the magnetic quantum number, this is what tells us the specific orbital. So remember, starting at the top, energy level, sublevel, now we're at orbital. And really all that magnetic quantum number tells us is the number of different values of M sub L tell us how many orbitals are in that sublevel. So that's why they span from negative L to positive L, because that will give us the exact number that we need. So if L is 2, negative 2 to positive 2, that's 5 orbitals. The D sublevel has 5 orbitals. The D sublevel is capable of holding 10 electrons, which again, if we go to our electron configurations, We know this to be true. The last quantum number, the spin quantum number, this is the one that designates a specific electron. This is where the Pauli exclusion principle comes in. No two electrons can have the same 4 quantum numbers. It's even if they're in the same orbital. If they are in the ground state, that lowest energy state, one of them has to be spin up, one of them has to be spin down. So one of them has to have a positive half level, one of them has to have a negative half level. If they're both spin up, we're in an excited state. If we're both spin down, we're in an excited state. And so the Pauli exclusion principle doesn't apply in those cases because the Pauli exclusion principle is describing ground state atoms. And saying that if I have an atom in the ground state in its most stable configuration, I'm not going to find 2 electrons that have the same 4 quantum numbers. I might have multiple electrons that have the same 2 quantum numbers. I might even have 2 electrons that have the same 3 quantum numbers. But I'm not going to have 2 electrons that have the same 4. So looking at questions 18, 19, 20 here, what can I say about orbitals within a given subshell? Well, if the subshell is given to us by L, then I know that at the very least, orbitals in that subshell are going to have the same energy and the same subshell. So they're going to have the same value of N and the same value of L. So that would be answer A, principal and angular momentum quantum number. The only way they would have the same magnetic quantum number is if those 2 electrons were in the same orbital. But that's not what it asks. It asks about if I have the same subshell. What are the possible quantum numbers when n equals 3? So if I'm looking at L, remember L starts at 0 and goes to n minus 1. 3 minus 1 would be 2 here. So 0, 1, and 2 are my options, which would be B. Which again, if we think about this in terms of a key, our electron configurations tell us 3rd energy level, 3s, 3p, and then after a little bit of an intercession from the 4s, 3d. There is no such thing as 3f. The reason there's no such thing is because we don't have the quantum numbers to support it. Right. Which of these sets of quantum numbers is allowed? Well, I need to look for obvious mistakes. So when we did this kind of an example in class, that was the thing I was trying to teach you then. Look for obvious mistakes. Look for n values that are negative, because we know that there's no such thing as a negative energy level. Look for spin quantum numbers that are anything but positive and negative 1/2. Now, in this particular instance, none of that is the case. So let's look for other obvious kinds of issues. L can never be negative. L starts at 0. So I know C is incorrect. With L equal to -1, I know that can't be possible. Are there any here where L is greater than n minus 1? Well, n is equal to 2, L is equal to 2? No, that doesn't work. N is equal to 1, L is bigger than it? That doesn't work. N is equal to 5, L is equal to, no, that doesn't work either. So by elimination, we would come up with B. Is B actually a valid set? Yeah, absolutely. We're talking about the 7s sublevel here. 7th energy level, S sublevel, magnetic quantum number of 0, which is the only quantum number that it can be in the S sublevel. Spin quantum number, that makes sense. Right. Right, other questions about quantum numbers? Yeah, Max?
What is the positive, like on question, what is that? What is that?
So what they're trying to trick you with there is for the ones that say positive and negative 1, 2, 3, they're trying to confuse you. The positive and negative 1, 2, 3 would apply if it was the magnetic quantum number, not the angular momentum quantum number. So that's where it's deliberately there trying to see if you are paying attention. So if we're talking about L, negative numbers never come into the discussion. But if we were talking about M sub L, then yes, M sub L would have negative numbers in it up to negative L and over to positive L. And so that's where D and E are being deliberately obtuse and trying to see if you really know the difference between L and M sub L. Right. More questions? Go ahead.
Process for like question 24.
Sure. All right, so question 24 is a question very similar to some other questions we've had to do. There was a question similar.
It's not showing.
Oh, wait, you said 24?
Yeah.
Okay. Okay. I forgot this one. Yeah. Okay. Okay, so this is an empirical formula problem with a molecular formula addition to it. So if you remember the process for empirical formulas, what we have to do is we turn the percents into grams, the grams into the moles, and then we compare. So if we did that, what's different about this one is this one has 4 elements in it instead of the 3 and 2 that we did in a lot of our examples. So 41.41 grams of carbon, 5.80 grams of hydrogen, 16.09 grams of nitrogen, 36.75 grams of oxygen. So our first step was to turn the percents into grams. The second step is to turn the grams into moles. For that, I'm going to need the molar mass of each one of these. So 12.01 for carbon, 1.01 for hydrogen, 14.01 for nitrogen, 16.00 for oxygen. Now, I'm doing it this way mainly because this is how I usually do it. I usually kind of go and do one set of calculations all the way through, and then the next set of calculations all the way through. You could easily go through each one of these in turn. So if it makes more sense for you to take the grams, do the conversion, punch the numbers into the calculator and get your number of moles, go ahead and do that. The only reason I do it this way is just, it's kind of just doing the same task over and over and over. For me, it's easier to get into a rhythm that way. And then I do all the calculations at once. So I'm not going back and forth, pencil to calculator, pencil to calculator. It's a style thing, really, more than anything. You know, more than anything here, you want to do you and do what makes the most sense to you. So first conversion, 4 sig figs 3.448 moles of carbon. Second conversion, 5.74 moles of hydrogen. Third conversion, 1.148 moles of nitrogen. Last one, 2.297 moles of oxygen. All right, last step here is comparison. What do we do from here? Right, before we round, we've got to standardize. So standardizing means we're going to take the number that's the smallest and we're going to divide everything by that number. If we don't do this, if we don't standardize first, then we don't have 1 mole of something to compare everything else to. And that's where when our numbers can get really kind of wonky and we can get a little bit too fun with all of the rounding. So out of this, I'm going to get 1 nitrogen. For the carbon, I'm going to get 3.003, so that will round to 3 carbons. For the hydrogen, I'm going to get 5 hydrogens, almost exactly. And for the oxygen, I'm going to get almost exactly 2 oxygens. So none of the numbers here, and this is a classic book problem, none of the numbers here came out to be anything drastically different from the whole number. I think the carbon was the furthest away and it was like 3.03. Certainly enough to round to 3 and not feel bad about it. If there were a fraction present in here, one of these comes out and it's like 0.5 or 0.33 or 0.25, 0.75, then we would know that we had to do one last manipulation to get rid of that fraction. But since that's not the case here, we just need to put these together into a chemical formula. So C3H5NO2 would be the empirical formula here. So that satisfies this part of the problem. Now, what about the molecular formula part? Well, here's where we got to do one more comparison. The molar mass of the actual compound is 174. What is the molar mass of this compound? Well, I've got to calculate it. 12 times 3 plus 5 times 1 plus 14 for the nitrogen and 2 times 16 for the oxygen. We get 87.03. If you're good at mental math, you already know what's happening next. If you're not, all you need to do is take that 174 AMU and divide it by the value that we just calculated, and we're going to get somewhere around 2. It's gonna be like 1.99 something. What does that 2 tell us? That 2 tells us that the molecular formula is double the empirical formula. So doubling everything, we would get C6H10N2O4. So if we're in the position where we have to do both, so module 2 quiz just asked you to do the empirical formula. But if you had to do both, what you do is you take that empirical formula and you calculate its molar mass, and you compare it to the molar mass of the other substance and figure out how different are they from each other. That comparison, that ratio is always going to be a whole number. And then you just multiply that whole number over your entire formula to get the molecular formula. All right, we've got time for a few more questions.
I would like to see any questions where we may get a half on the numbers we get there.
I would say it's possible. If you did, then you would just, like I said, you just need to extend that calculation one step further. So let's just say, for argument's sake here, that instead of 5 hydrogens, it came out to 5.5 hydrogens. Well, all that we would have to do is, obviously we can't make this formula 5.5 hydrogen. We would have to multiply the entire formula by 2 to get rid of the half fraction. So kind of similar to what we were doing yesterday with combustion reactions. If we have a coefficient of 1/2, we multiply the whole equation by 2 to get rid of the half. Same kind of idea here. If I do the calculation and it comes out as 1/2, I multiply everything by 2. This would have been C6H11N2O4. And then you would just compare it to the formula to figure out the molecular formula. In that particular case, you would have got 175 as the molar mass for that empirical formula. And so you said, okay, 175, 174, they're basically the same. The empirical formula must be the molecular formula. And that's always a possibility. Empirical and molecular formula can be the same. They do not have to be different. But if they are different, the molecular formula will always be the bigger formula. Go ahead, Kim.
Percent errors.
No, I don't think percent error will show up on this. That's really not a concept we've done other than in lab. So that might be something to stick in the back of your mind for a lab final, but not here. Max?
Will we have to use the library equation?
It's possible that you'd be asked to do one of those energy calculations. And so what's important there with the Rydberg equation is just making sure that you know what it means, and so that you know what each of those variables are. So remember, your equation sheet has the value of RH on it. So that you can just sub in directly. It would become a matter of you knowing, okay, what is lambda? Lambda is the wavelength. What does N1 and N2 mean? Well, those are the energy levels that we're starting with and ending with. So that's why we give you this equation sheet. So if we ask you a question along those lines, you don't have to memorize the formula, you just have to know how to use it. Go ahead.
Remind me again, how much did the 174
So the 174 came from the problem itself. It told us that the molar mass of the molecule was 174. And you can't do a problem like this without knowing the molar mass. You can't figure out an empirical form, or excuse me, you can't figure out a molecular formula from the empirical formula without a molar mass, because you have to know what you're comparing against. All right, go ahead, Ethan.
Go over electron configuration when it doesn't fill up the whole orbital again. So this is where you take it actually at the S instead.
Okay. All right, so let me pull up a periodic table here, because that'll probably help the most. So just to remind ourselves here, the areas of the periodic table that have those exceptions are primarily the D4. Okay, not that way. So the D4, the D9, and large chunks of the fifth, that fifth row's D sublevel. And the reason behind it is a matter of stability. So in the case of D4, we have 5 orbitals and we've got 4 electrons. So for whatever reason, taking one of these electrons from the S and moving it over creates that extra stability that we've been talking about. So in the case of chromium and molybdenum, basically those 6 orbitals have basically the same energy, and so they spread out. So it's kind of a long form explanation of Hund's rule. Where Hund's rule says that if I come up to a sublevel, all of the orbitals in that sublevel are all of equal energy. So the electrons are going to spread out. Well, when it comes to the D4 and the D9 configuration, that's more or less what's happening. The S orbital and the D sublevel are basically the same energy in those configurations. And so as a result, one electron hops over to fill the larger sublevel because the larger sublevel will have more stability with every orbital filled out. And it's roughly the same idea, kind of in large scale when it comes to palladium. Remember, palladium is actually S0. Both of the electrons in palladium jump. And that is actually probably the weirdest phenomenon, because what that's actually saying is that I've got my 5s and my 4d, and usually I would think of them this way, 5s being lower in energy than the 4d, but for palladium, it actually flops. The 4d is lower in energy than the 5s, so all 10 of those electrons jump into the 4d, and none are left over in the 5s. And considering that most of these anomalies, if you look at the configuration for the 4D sublevel, we can kind of make a general conclusion in that regard. The 4D sublevel is lower in energy than we think it should be. And that's why so many electrons hop over. Because out of the 10 elements in that group, 6 of them have exceptions. And of the 4 that don't, we can rationalize 2 of them. None of the D5s have exceptions. And it makes sense why they don't. That D sublevel, completely filled. Half filled, but each orbital has an electron in it. The D10 sublevel, completely filled. Nowhere for those extra electrons to go. The only ones that don't participate, that don't have that kind of an explanation, yttrium and zirconium, the D1 and the D2. And at that point, what would they gain by adding that extra electron? Going from D1 to D2, that's really not going to increase the stability at all. Going from D2 to D3, again, really not going to increase the stability that much. But for whatever reason, yeah, going from D3 to D4, that seems to be a difference. Going from D4 to D5, we've got a lot of evidence to show that. Going from D9 to D10, absolutely. So this is where we really want to leverage the periodic table to our highest advantage. Recognizing that the exceptions are patterned, that it's not just a random kind of conglomeration of electrons moving. They seem to be moving intentionally and with purpose. And we can explain most of them, and when we actually graph it onto the table itself, it makes a lot more sense. Which is one of the reasons why I told you at the time, grab that periodic table, draw this stuff in, because it's going to help to have that picture that you can kind of burn into your head, and it automatically kind of translates onto the periodic table, even if you don't draw it in yourself. All right, got time for maybe 2 more questions. Go ahead, Mass. All right, 22. Okay, so this is one I was halfway down the last time you asked me a question. Okay. So the process for this is, remember, we're going to take percent and we're going to multiply it by the mass for each of the isotopes. So if you're familiar with mathematically the weighted average, this is a weighted average basically. So I would take my first percent, 78.99, and multiply it by the mass, 23.985 AMUs. I would take the second percent, 10.00, and multiply it by the second mass, 24.986 AMUs. And I'd add that to the third percent, 11.01, multiply that by 25.9826 AMUs. Okay, so this is where you'd have to use your intuition here. You could turn them all the percents into decimals first. You could do that. The reason I don't do that is because I find that it's easy to make a mistake in the conversion and not move the decimal place the correct number of places, and make a mistake that is super easy to make and will definitely lead you to the wrong answer. When you do it this way, you're going to get an answer that doesn't make any sense. You're going to get a molar mass that is in the thousands. And obviously molar masses aren't in the thousands. So that's when you have to kind of rely on your own mathematical intuition and go, oh yeah, those were percentages. I got to divide by 100. And then the thousands turned into hundreds or tens. And you go, oh, that matches up with one of the things on the periodic table. So in this particular case, this ends up matching up with magnesium. So if you want a full write-up of that answer, again, check out the key, which will be posting here in about 20 minutes. Max?
So all these calculation questions, well, like on the district file, will they be like the same?
So I can't guarantee that you're going to get the same exact style of question. What I can guarantee is that the questions will be formatted similar to this. So chances are pretty good you'll get an empirical formula question. Chances are pretty good you're going to get some kind of conversions question, because that was kind of the big idea out of that first module. Chances are pretty good you're going to see some kind of question related to light, energy, frequency, something along those lines out of module 3. Chances are pretty good you're going to see some kind of electron configuration, because we spent a good amount of time on electron configurations. So if you kind of look at the topics that were covered in those quizzes were kind of the big ideas. Now, some of the quizzes I couldn't cover everything, which is why, the module 3 quiz didn't give you calculation questions on there. I thought that there were more relevant things to ask. Tomorrow, there's a good chance you'll see some kind of module 3 calculation. So know how to use those equations. But no, don't expect that the format of the exam is going to be identical, and then I'm just going to change the numbers on you. That might be how things were in your high school classes. That's not how things usually work at the college level. There are way too many questions. I'll tell you, exam writing is one of the hardest tasks I have, because I have to take 5 weeks of worth of material and condense it down to something that you can give me in 45 minutes. It's a tough task sometimes. And often I will write exams that end up being way too long at the start, and I have to trim them back. And that's why I take every single one of the exams that you take first to get an idea of how long it should take you to do it. So before we part for today, let me just remind you of some resources that might be useful to you if you're looking for additional practice. So you already know about this practice exam. You already know about the practice assignments in Top Hat, where you could get specific kinds of questions and get feedback on those questions, based on your answers. Now, I know that the feedback in Top Hat is not nearly as robust as what was in Active, but it is a place to get extra practice problems. You also have in Active, you can go back through any of your homework assignments and look back at those again. And there are those 2 extra practice modules that I put in based off of the most asked questions out of module 2. So if you want more empirical formula practice, if you want mole conversion practice, there are extra modules in Active that aren't worth any points, but are there for your practice. The other thing that I would remind you about is Chem Quiz. These quizzes are available to you. You do not need to sign up for anything. But if you're looking for additional kinds of problems where you recognize, boy, I'm really having trouble with this, you have the ability through Chem Quiz here to go back and look at extra practice problems. And remember, this is self-generative. So if you want extra electron configuration practice, you can make yourself a little 10-question quiz. And just write it out. Put in your answers, hit grade it, and it'll tell you what the correct answer is. It'll give you both the noble gas and the complete configuration, and it'll tell you in some cases, so like, you don't have to worry about lanthanum being something you'll see. I already told you anything the F block is off limits. But it'll tell you if it violates what's called the Madelung rule, which is what we are just calling anomalies or exceptions. So, why does palladium not have a 5s2? Well, we discussed that. It's one of the exceptions. So it gives you that information there as well. It allows you to regenerate new questions, new configurations, as well as, going back to others. So you have, between all of those resources, probably about as much practice material as you could stand. Let me give you a couple of pieces of advice, a couple of tips here. Don't spend all night trying to do this. As much as cramming gets a certain reputation as being something that is just done by college students, is about the worst thing that you can do for yourself. You know, if you got the 9 a.m. lecture and you spend all the way up until 9 a.m. studying for it, there's a good chance that there isn't going to be anything left of you at 9 a.m. to actually fill out the test. Get a good night's sleep. If you want to come back to it in the morning, come back to it in the morning, but make sure that you actually give yourself proper rest. Make sure that you're practicing by doing, not just by looking. Your notes are great. Hearing me and other YouTube people talk about it is fine if you're trying to fill in the holes. But more importantly, especially on that calculation stuff, you've got to be able to do it. So get yourself in front of practice problems and get a pad of paper and something to write with, a calculator nearby, and scratch it out. And then finally, make sure that you are aware that there is a calculator limitation. You have to have a scientific calculator. Graphing calculators are not allowed. If you don't have a graphing calculator, check in over at the learning lab before class. Go ahead and borrow you one. They'll trade you something for it, usually your ID. All right.
Sorry.
All right.
Yeah, I'm good. Sorry.
It's okay. I'm more worried about you. They'll trade you for your ID. No big deal. Just, go back after the exam, trade it back. But if you show up with a graphing calculator, I'm going to tell you to get a different one because the final exam is calculator restricted. So we're practicing for that. So just be aware of that. Any final questions for me?
It's like these are not allowed.
Those are not allowed, correct? Yeah.
Is the whole class going to be taking up by the exam, or are we going to do a bit of lecture?
There will be no lecture. So, like I said, we will start at noon in your case. Whenever you're finished with the exam, you'll just turn it in and you're done for the day.
Okay, because I had some questions about stoichiometry that I wanted to ask, but I didn't know that.
Okay. Okay.
So are we in class or in the testing center?
So in your case, you'll do it in the testing center so that you get the time accommodation.
I'm not sure if you mentioned it earlier. How long does they have questions?
I believe it's 24. The majority of those are multiple choice, and then there's a handful of these kind of questions that we spent most of our time on at the end. So I want to say it's 15 multiple choice, and then like 6 or 7 or 8 free response after that. And you should know also that the exam is overscored. And what I mean by that is there are 88 possible points, but you're only being graded out of 80. So take that for whatever you want it to mean. If that means that you want to skip a question because you don't know how to do it, that means that you can skip a question because you don't know how to do it. Just don't skip a question that's worth 12 points when you only get 8 points for free. What usually happens though is that people will try every question and hope to get bonus. And so anything that you score over 80 does get added as bonus. And that does obviously improve your grade. And so that'd be the other thing that I would say is that, right now your grades in Blackboard aren't really a good representation of your status in the class. And that's because we haven't had an exam yet. So once that first exam grade gets in there, the grade will kind of reset itself to match a little bit closer to what your actual performance is in the class. Right now, it's very heavily skewed by 2 things. Are you doing every homework assignment? Then it's skewing high. If you haven't passed every proficiency yet, it's skewing low. And so if you're in both camps, it's putting you somewhere around a C or a D, and chances are you're at neither. So like I said, once that first exam grade goes in there, the grade will kind of recalibrate itself because now it'll have an actual exam to base your grade off of instead of estimating what your exam percentage would be. Because that's what it's doing right now, is it's guessing based off of your quiz performance and your other things. All right, any last questions? All right, thanks for coming in today. I'll see you tomorrow. Carlos, you have a second? You have a second?
Yeah, sure.